right, we're looking at an old final exam optimization question. So this is from December 2018. And so as we do these questions, I'm going to kind of highlight the steps here. The first thing for optimization is that you need to check for constraint equation. Sorry, constraint equation. And you also need an optimized function. Right, so this should be the first two things you're thinking about before you even start to draw a diagram. Just look at the word problem and see what kind of things am I looking for. So it says you plan to make a box with a square base and lid with largest possible volume. So you see the word largest or smallest or minimize or maximize. That should clue you in that you are what you're optimizing. And then as you keep going with the statement, it says that with a surface area of 140. So anytime you're given a geometric object with a specific numeric value, that will be your constraint. All right, so we're going to keep these two things in mind. I'm going to move them up a little bit. Okay, so now this is where you start drawing a diagram. So I'm going to draw it here. We have a rectangular box with a square base. So that means that the length and the width are x, and then the height is equal to h. Okay. So now in this case, volume, which is length times width times height, will be x times h. Right, and then the surface area, which they said was 140, will be the length, the area of the top plus the area of the bottom. Right, the top and the bottom are both x by x squares. And then the four faces, you've got x by h in the front. Same thing for the back. And then you've got the left and the right faces. And the right face is x by h. Same thing for the left. Right, so this is top. This is the bottom. This is the front. This is the back. This is the left. And this is the right. So if you put them all together, combine your like terms, you get, I'm going to move this over. You get 140 equals 2x squared plus 4xh. Okay, so this is just playing around with these two pieces here. Ultimately, I want to be working with the volume, and it says your function should contain the variable x and no other variables. Right now we have v is equal to x squared h. So what I need to do is I need to get rid of this h variable. And you do that by working with the constraint. So solve for h here. Right, so I'm going to subtract. Let me do that. 140 minus 2x squared equals 4xh, and then divide by 4x. 140 minus 2x squared over 4x equal to h. So now that gets plugged in for h. X squared times 140 minus 2x squared over 4x. Okay, so this is now your answer for part A. You have a function in terms of one variable. Right. Just to recap what we did, remember, first thing is go ahead and start thinking about these two things: constraint equation and optimized function. Right. By keeping that in mind, going through your first read through, you'll see, well, this is what I'm trying to make biggest or largest is volume. And then the constraint I have, the numeric surface area, is what I'm going to be able to use to get rid of a variable. And now normally if we were to stop here, I would just let's erase that. What I'm going to do is I'm going to go ahead and simplify this. This is x squared over 4x. So this is an x, right? One of those cancels. 140 over 4 is 35. 2 divided by 4 is 1/2. Right. So I cleared out this x, and then this 1/4 essentially divided the numerator by 4 to give me that. Then I'm going to keep distributing this. This is volume is equal to 35x minus 1/2 x to the third. All right, so we have a polynomial. Ultimately, the next step would be to find critical points, which is why I'm cleaning this function up. Right. Part B says determine the domain of your function. So my function v of x is 35x minus 1/2 x cubed. Now, of course, this is a polynomial. The domain would be all real numbers, but in this case, remember that this is measuring the volume given the length x, right? Well, x can't be negative. It also can't be 0, right? If you have 0 length, then you have a 0 volume, which is not gonna work. That means that your domain will start at 0, and then keep in mind this constraint equation. This constraint equation helps you get rid of the variable h in the volume function, but it also tells you how big, as x gets big, what's going to happen is that h gets really small. Right? If you use more of the dimensions on the length and the width, the height gets shorter and shorter. So what we're going to do is we're going to use this constraint equation here. Equal to 0, so we have 140 minus 2x squared over 4x equals 0. All right, so if we multiply both sides by 4x, you're going to get a 0. So 140 minus 2x squared equals 0. 140 equals 2x squared. Divide both sides by 2. All right, so root 70 is the largest that x can be. That gives me my relevant domain. All right, so this is your domain. Now, this is a cubic function, but we're going to constrain it to just 0 to root 70. Finally, we're looking for the largest possible volume. So we're given the volume function. Let me scroll up to 35x minus 1/2 x cubed. Right. The next step would be to find a critical point. All right, so b prime is 35 minus 3/2 x squared. Right, we set this equal to 0. Okay, I'm going to multiply by 2, divide by 3. and then take the square root. So we got critical point of root 70 over 3. Right, we would use just a minus because my domain was negative. Sorry, not negative infinity. The domain was 0 to root 70. Right, so this is the only critical point we have. And so there's a couple ways to check that this is a maximum. Right? Critical point could be a maximum, could be a minimum, could be not an extremum. And so in this case, what I'm going to do is I'm going to use the second derivative test. This is a negative 3x. That's my second derivative. And so now if I plug in the critical point, I'm getting a negative 3 times root 70 over 3, which is negative, right? That's the really main thing I want to care about. So that means that we have a concave down graph. Right, so that means that the second derivative test tells us it's a local max. Right. So this is what they mean by saying you must use calculus to verify the volume. All right, so this is the verification that we're using, that we're checking that it's actually a max. So the final answer in this case is the volume. We take this root 70 over 3, plug it into this volume formula. All right, now you can leave your answer like that. The answer would be in inches cubed. All right, if you want a decimal approximation, which you don't really need here. Right, so I'm getting roughly 112.7107 inches cubed. That's my final answer.